All right, welcome to Codex. Today we are very happy to have Professor Dustin Mixon. Professor Mixon is an assistant professor of mathematics at The Ohio State University. While serving in the United States Air Force, he earned his master's degree from the Air Force Institute of Technology and his PhD from Princeton in 2012. He was an assistant professor at the Air Force Institute of Technology until 2017 when he moved to OSU. Since 2006, Professor Mixon has published over 50 research articles in numerous fields. I want to mention a few here, but this is by no means an exhaustive list. In frame theory, he's made significant progress on some fundamental questions on the existence and structure of type frames, in particular unit norm type frames, equiangular type frames, and type fusion frames. In phase retrieval, he has advanced our understanding of the minimal number of measurements required in a complex vector space. Professor Mixon has also worked on clustering, compressed sensing, the mathematics of gerrymandering, and he coordinated Polymath 16 on the Hadwiger-Nelson problem in geometric graph theory. Anybody that knows Dustin knows that he loves working on math, especially working with other people. While he has a long list of frequent collaborators, amazingly, he's also averaging approximately one new co-author per article published. Today, Professor Mixon will tell us about some of his recent work on packing problems in compact metric spaces. In particular, he's going to discuss the interplay between optimality and symmetry in these problems. Take it away, Dustin.
Wow, that was a great introduction. Thank you so much. I want to thank my co-organizers for forcing me to fill a hole in the Codex schedule. This is going to be fun. Okay, here we go. Some work that's been sponsored by NSF and AFOSR. The motivation is really coming from some inspiring work by Fayez Toth. I assume that's how I pronounce that name. If someone knows better, please correct me. Fayez Toth. So he pointed out, I have a comment. Maybe that's
just the link to the mailing list.
Be sure to sign up for the mailing list. I hear that this seminar is awesome. Fayez Toth, he pointed out that there are these things in the world that he called regular figures. So you should be thinking about like platonic solids and pretty things like that. Platonic solids have been around since, I guess, Plato or something. Euclid in his Elements constructed all of them. You can kind of prove to yourself that those are all of them. It doesn't take too much effort. I think a high schooler could do that. Maybe you should do that in the shower or something. Think about why all of the existing platonic solids are actually all of the platonic solids. And this is an approach that mathematicians take. We identify something that's pretty, and then we're like, hey, let's find all the pretty things under that definition of pretty. So enumerating all regular figures is kind of a classical way of interacting with these objects. And he called this systematology. It's kind of a mathematician-oriented approach. Like the mathematician makes a definition, and then he enumerates everything that satisfies that definition. But he also pointed out that there's another more natural notion of regular figures, this theory that they arise naturally from optimization. So it kind of takes the mathematician out of the loop. It has nothing to do with the fact that there's an observer. It's just that these beautiful things emerge in nature on their own. And that's kind of motivated a lot of what this work goes into. I wanted to share with you some of my favorite examples of this. So one of them is efficient decomposition into cells. So you're given this unit square, right? And I give you a number n, and you need to partition that unit square into convex polygons. All of them have to have the same area, but I want you to partition it in such a way that you minimize the total edge length, okay? So the total number of, you're imagining maybe you have this region, and you have to build walls so as to partition the region into portions, into cells of equal area, but you want to minimize the amount of wall that you're using. right? And if you're thinking in terms of like the isoparametric inequality, maybe you remember that the most efficient way of encircling space with a given perimeter is to actually take the space to be a disk. And you can't really partition a square into disks, like disks don't tile, but you can get close. And in fact, you get what the bees figured out is the right thing to do, namely to break out the space into these hexagons. So it's not entirely obvious that the bees are trying to optimize this particular objective function of minimize the amount of wax it takes in order to break out this region into equal size cells. But they are, it's reasonable that they're optimizing something. And it's interesting that Fayez-Toth was able to prove that this was optimal. Some other examples, this is an example from recent math literature, the Erdős distinct distances problem. So I give you n points and you have to arrange them in the plane in such a way that the set of distances between pairs of points is as small as possible. So like a triangle, if n equals 3, you can get away with one distance with an equilateral triangle. If I give you n points, how small can you make the distance set? And these are arrangements that are optimal for their number of points. And you'll notice that they all, I mean, these circles obviously exhibit symmetry, like there's a rotation symmetry. This object right here, you might argue, only has a reflection symmetry. In general, you might end up with an object that has no honest symmetries, but it will necessarily exhibit many partial symmetries, which is to say that there's going to exist a lot of members of the Euclidean group that send the set not necessarily to itself, but to something that intersects a lot with himself. In fact, this feature was used by Guth and Katz in order to all but solve the distinct distances problem. Another example, sphere packing. You can pose it as a problem of maximizing the upper Berling density of points in Euclidean space, where every pair of points is not too close to each other. If you try to optimize this thing in certain dimensions, you get the sort of arrangements that you would expect. These are the sorts of arrangements that you'd find oranges being placed in at a supermarket. So it's kind of an obvious packing. In fact, in many dimensions that, like all of the dimensions that we know how to solve this thing, optimizers happen to be lattices. Well, the more correct thing is that lattices happen to be optimizers. And it's conjectured that the solution in 4 dimensions is also a lattice. The thing that's probably closest to what we'll be talking about is this example from spherical codes, where you're given a number of points and you have to arrange them in the sphere so that you maximize the minimum distance. So this was posed by a Dutch botanist. He looked in his microscope and noticed that these pollen grains had these dangly things hanging off of them that it seemed like they wanted to be spread apart from each other. So he wanted to be able to formulate predictions. So he posed this math problem that says, how do you maximize the minimum distance? We'll model this grain of pollen by a sphere and see what comes out. And Fayez-Toth came along to prove that this collection of platonic solids happens to be optimal for their number of points. And in the time since, we've found more solutions to this Thomas problem. Yeah, so today we're going to be thinking about a generalization of the Thomas problem where it's not necessarily packing points in the sphere, but rather in an arbitrary compact metric space. This is an abstract coding problem of I want to maximize the minimum distance if I'm given a particular number of code words, a number of points. And the way the talk is going to be organized is the first talk will think about how, like, under what conditions can you say that symmetric codes, codes with lots of symmetry, are necessarily optimal codes, that they solve this optimization problem. And then the second part will go in the other direction. We'll think about in what sense can we say that optimal codes are necessarily exhibiting symmetry? So kind of a converse. Any questions before we hop into the first part? All right, let's do it. Part one, symmetry implies optimality. This is joint work with one of my co-organizers, Joey Iverson. That's a nice looking picture. Cool. So let's start with a general proof technique. You want to show that symmetry implies optimality. Let me tell you a nice way of doing that. It's going to factor through a design condition. So you start by observing that some condition implies optimality. Okay? So you have to solve the optimization problem and understand, oh, this is what optimizers look like. And once you've identified a design condition that implies optimality, then you figure out what sort of symmetry conditions imply that design condition. Okay? That's the big idea. So a simple example is our metric space is the unit circle. Okay? And a pigeonhole argument tells you what the design condition ought to be. You actually want the points, the endpoints that you're given, to be uniformly spaced along the boundary of that circle, along that circle. So this is actually equivalent to being optimal as a packing in this metric space. And if you want to figure out a symmetry condition, well, here's an example of a symmetry condition that implies optimality. In fact, it's equivalent to optimality. If you look at the symmetries of your point set as a group, so this is so OT of P is the set of all permutations of P that can be realized by a member of the isometry group of M. Okay, so this permutation group is going to be a subgroup of the dihedral group. And it turns out you get equality precisely when your point set is optimal as a code. So the reason, it's obvious that he's going to be in the symmetry group on n letters, just because there's n objects floating around. But the reason he has to be in the dihedral group is that the ordering of the points has to be preserved, at least up to reflection. The ordering of the points along the circle. Another example is you could say that P is optimal if and only if there's a subgroup of the special orthogonal group that acts transitively on P. So obviously, uniformly spaced points has this property. But if you have this property, then you know that this subgroup that acts transitively is going to have to be finite, and every finite subgroup of SO2 is cyclic. So then you take the orbit of some point, and that gives you uniformly spaced points. So symmetry implies optimality in this special case. Another case, we'll look at those spherical codes, but we're going to focus in on the special case where the number of code points is dimension +1. So if you're familiar with the Rankin bound, you know that the optimizer here is precisely the vertices of the centered regular D simplex, one of those Platonic solids I showed you earlier. If you want a symmetry condition, you can get things that look like the previous slide. The symmetries of P are going to be a subset of Sn with equality precisely when you're optimal. And also, you're going to be optimal if and only if there's a subgroup of the orthogonal group that acts doubly transitively on the point set. So what doubly transitive means is for every pair of ordered pairs of points, there exists an isometry that permutes all of the points, but in particular, it sends the first ordered pair to the second ordered pair, doubly transitive. So it's transitive, but even more, it sends pairs to pairs. Great. So the proof of this is you open up you look at what the gram matrix looks like of these points. You know the off-diagonal entries have to be all equal because you're doubly transitive. You're sending all pairs to all other pairs, so the angles have to be the same. It's positive semi-definite, but it's also rank deficient because you have d+1 points in d dimensions. And so that forces what A has to be. Great. And now the case that you've all been waiting for, complex projective space. So if you're given more points than the dimension, so a design condition would be equiangular tight frame. This isn't an if and only if, but it's a sufficient condition for optimality. If your points happen to be an equiangular tight frame, then you're optimal. And what that means is your lines have unit norm representatives that are equiangular in this sense. So the modulus squared of the inner product between any two of those representatives is a number alpha. And then the sum of the outer products is going to be some scalar multiple of the identity. That's what tight means. And it turns out by an argument not too different from the previous slide, if you have a subgroup of the projective unitary group that acts doubly transitively on your point set, then your point set forms an ETF for its span. Okay. So this is a symmetry condition that implies optimality. So the previous examples were kind of less interesting maybe because we already understand optimal spherical codes, like at least in the circle, and we understand that the simplex is optimal. Not interesting. But these equiangular tight frames, this is a area of active research. So this sort of implication kind of insists upon a certain project. This systematology that Fayez Toph may have called it. We've identified a notion of a regular figure. So now let's enumerate all regular figures. Let's find all possible doubly transitive lines. Okay. These are going to be optimal codes in projective space. In fact, they're going to be equiangular tight frames, and they're going to be more than just equiangular tight frames. They're going to have all this symmetry. So in the real case, so if your lines are actually sitting in RD instead of CD, this classification was done by Taylor. And what he wasn't thinking about lines, he was thinking in terms of these combinatorial objects known as two graphs. And if you're familiar with equiangular lines, you're familiar with their correspondence with two graphs. And he was particularly interested in doubly transitive two graphs for historical reasons. And he was able to classify that. In another extreme case where the number of points is actually d squared. So in this case, your equiangular tight frame is known as a seq, a symmetric informationally complete thing. And these objects, these doubly transitive seqs, were characterized by Zhu. In fact, these are precisely the seqs that appear in dimensions 2, 3, and 8 that are kind of oddballs. They're sporadic compared to all the other constructions that we know about. So in order to close the gap to get all the other cases, this is the idea. It turns out that all doubly transitive groups are known. They've been classified. This comes as a consequence of the classification of finite simple groups. Okay, so there's a list of doubly transitive groups, and those are all of them. So the idea is we'll just iterate through the list, and for each doubly transitive permutation group, can you recover the lines from the symmetries? That's the question. So I'm giving you a group, and I'm asking you to figure out what are the lines whose symmetries include that group. It's kind of a weird question. It's like an inverse problem or something. So let me talk you through this. So for this slide, I want you to think of the lines as not being points in projective space, but rather they are sets in Euclidean space that go through the origin. And we're going to be thinking about the union of those lines. So that's a subset of Euclidean space. And we're going to think of some abstract group acting on this set, okay? So when it's acting on the set, it's going to be moving points in the set to other points in the set, and really it's going to be permuting the lines, right? But there's going to be a subset of, in fact, a subgroup of this group that for some line, every point in that line is going to be fixed by each member of that subgroup H, okay? I'm not saying that the line is invariant under the action of H. I'm saying something stronger, that every point in that line is fixed under the action of H, okay? So given G and H, we're going to recover the set of lines up to rotation. That's the idea. How do we do it? Here's an example. I have this abstract group, SL25, so 2 by 2 matrices with entries in F5. And then I have a subgroup generated by this 2 by 2 matrix. Once I'm given this data, I'm going to scroll through representations of G. So for example, here's a representation of G. This representation sends these 2 by 2 matrices over that finite field to 3 by 3 matrices over the complexes, okay? And this number phi here is the golden ratio. So this is a perfectly good representation. Once I have it, I can look at how H acts on the space in under this representation. So in fact, I'll focus on all of the points in 3 space that are fixed by everybody in H. Okay, this is a candidate for this line that was promised is fixed by H. And once I have that line, I can spin it up with all of G. And in this case, what you get, you actually recover the planted 6 lines in R3 that make up the diagonals of the icosahedron. So that's the idea for how to recover lines from symmetries. If you go through this program with doubly transitive lines in mind, then you'll actually notice some necessary conditions that G and H have to satisfy. And you can distill that algebraic structure. And when you do that, you'll come up with a definition. You'll get this definition. So you have G, H. What K here represents is the group of symmetries that leaves that line invariant. So you're not just fixing each point in the line. You're mapping the line to itself. Maybe you're reflecting it or you're phasing it up somehow. And G and H together will be called a Higman pair if they satisfy these conditions. So G mod K can be thought of as the lines. This is the same as the line. So G is acting doubly transitively on the lines, and I have these other conditions that need to be satisfied. It's a Higman pair, and it's named after this pair of Higmans. Cool. That dad joke came from Joey, by the way. So you can thank him for that. Great. So once you've distilled this algebraic structure, you have a notion of a Higman pair, you can prove this theorem. And what this theorem says is a Higman pair is the correct object for doubly transitive lines. If you have a Higman pair, then you can pass to any irreducible representation of G. Remember, we pass to a particular 3-dimensional representation. Take any irreducible unitary representation and turn the crank. That set that I called L, it turns out for every irreducible representation, it's either going to be a line or just the set containing 0. And if it's a line, you take an orbit and you'll end up getting doubly transitive lines. You'll get doubly transitive lines for every irreducible representation of G for which L is a line. So you could conceivably end up with doubly transitive lines coming from a group that are in different spaces. That's kind of interesting. The converse here is that if you have doubly transitive lines, then you can actually be recovered from this machine. This is a characterization of doubly transitive lines. Higman pairs are the correct object. So now that we understand the correct object, you could imagine turning a crank where, well, I have this classification of doubly transitive groups. Given a group, I hunt for a Higman pair, and then I recover lines using that machine. So there's a natural bifurcation of sorts of these doubly transitive groups. Burnside showed that every doubly transitive group is either almost simple, which means it's damn near a simple group. Not necessarily a simple group, but it's close to being simple in some sense. Or it's affine, which is to say that it's something like an AX plus B group, okay? So there's this two different types of groups, and it turns out that our theory is, it's easy to turn our crank for these almost simple groups, and it's less easy to turn for the affine groups, and I'll explain more on that in a moment. We turned the crank in the almost simple case, and we got this classification. So if you have doubly transitive lines, and they have almost simple symmetries, then they are one of these constructions, okay? And so now you're wondering, what about the other case? So this is where the problem emerges. So this doubly transitive group is, this should be thought of in terms of the projective unitaries, okay? Because I'm spinning up, I'm permuting lines, okay? So I'm ignoring phase when I permute lines. In order to use the Higman pair technology, I remember this arrow is the Higman pair theorem. So if I want to use the Higman pair technology, I need to be thinking in terms of honest unitaries, not projective unitaries. So what that means is I need to bridge the gap between these projective unitary objects and the unitary objects. I want to access an honest representation, not a projective representation. So the arrow you go through in order to do that is you have to pass through a Schur cover of your doubly transitive group. And in the case of almost simple groups, these Schur covers were obtained in the classification of simple groups. Like this was one of the objects that helped them classify things. In the affine case, you might be scrappy in some places to cook up what a Schur cover could be, but in order to get something for the entire classification, we're going to need some help. So some perspective, briefly, is that you could imagine a ladder of symmetries where the higher you are on this ladder, the more symmetries you have, and maybe that helps your cause in finding these optimal projective codes. So in this rung of the ladder, we have double transitivity. In terms of, there's a really nice picture in terms of Gram matrices where for a fixed group, if you're spinning up with a doubly transitive group, you can look at the Gram matrices of all possible orbits. And then that space of Gram matrices forms in algebra under matrix multiplication. And it's actually commutative. So by the spectral theorem, there's a convenient basis of idempotence, primitive idempotence. And for the doubly transitive story, it turns out that the Gram matrix you want that corresponds to the ETF is a primitive idempotent of that. So you know exactly where to look for these objects. If you ask for more symmetry, maybe you want triply transitive lines. And in this case, you end up with orthonormal bases and like the simplex, really boring objects. So you're asking for too much going upstairs. You can descend down the ladder. Maybe you ask for that same commutative algebra structure, but maybe the Gramian is not necessarily a primitive idempotent. Maybe it's just some other combination of primitive idempotents to make an idempotent. And this is the formalism where different sets reside. There's a finite search because you have to figure out which combination of idempotencies to combine in order to get your gram matrix. But it's finite, so it's good. If you descend even further, you end up with a non-commutative algebra of matrices. So hunting for the Gramian amounts to an infinite search, at least from this perspective. There's no signal for what a good Gramian is, and this is where Zauner's conjecture resides. There's not enough symmetry in order to make things go under this perspective. So we're interested in doubly transitive lines with affine symmetries. We're also interested in tackling other instances in which symmetry implies optimality for like other compact metric spaces. So that concludes the first part of my talk. Are there any questions about this part before I move on?
Is it, are you willing to talk about some of these other instances of symmetry implies optimality, or is this sort of like a potential thing you might work on in the future?
It's the things that exist here are not public. So, but there do exist interesting things in this world. So, yeah, other questions? All right, moving on. Optimality implies symmetry. This is joint work with a cast of characters, Chris Cox, Emily King, who's a co-organizer of Codex, and Hans Parshall. So I want to start with some intuition here. Remember, we're trying to get optimality implies symmetry. So you're optimizing a thing, and then symmetry is some emergent feature. Okay. So in order to give you some of this intuition, I want you to think about optimal spherical codes. So we're packing points in the sphere. This is like the Thomas problem, but also in higher dimensions. There are phase transitions in this world. So if the number of points is somewhere between 2 and d+1, we understand what's going on here. This Rankine has the simplex bound. It characterizes a quality. It makes a lot of sense, well understood. The next regime is when the number of points is between d+2 and 2d. In this world, you have Rankine's orthoplex bound. So these optimizers, like examples of optimizers are the full orthoplex, and then just remove vertices from the orthoplex until you go down to d+2. All of these are optimizers for the spherical code problem. Okay, so now we're up to 2D points. If you add one more point, then we're in the realm of conjecture. So there's a paper down here, Henry Cohn and others. They conjecture that this particular construction is a general construction for all D that works in general. So what it is you have the North Pole, and then you have a simplex of lower dimension on this line of latitude, and you have another lower dimensional simplex that's kind of dual to that one on this other line of latitude. So you pick the lines of latitude that make the distances work out. They conjecture that that's optimal, and it's only known to be optimal for D = 2 and 3. For D = 2, it's the pentagon. So then if you ask for more points, it's really hard. We don't know what's going on up here. There are a few examples where like there are these sporadic constructions that have enough symmetries that you could actually prove that they're optimal using certain techniques. There are no infinite families of ensembles for which we understand, for which we have proofs of optimality. There are no conjectural optimal infinite families. We just know nothing up here except for finitely many constructions. So the intuition I want you to take out of that is that there's something of a dichotomy here, where for some of these packings you have symmetry, and for other optimal packings you have complexity, and these two things appear to be at odds with each other. Okay, so there's a tension fundamentally between complexity and symmetry, something that we ought to consider when formulating a hypothesis on how optimality somehow implies symmetry. Okay, some more intuition. I want you to think about points, spherical codes that are optimal in the orthoplex regime, but I want it to be the orthoplex, size of orthoplex minus 1. So if you remove the bottom vertex of the orthoplex, you're left with this packing of 5 points in the sphere, and this happens to be optimal. If you take this point and slide him south towards the South Pole, he's still going to be optimal. And you can do that until he becomes the South Pole. This is a continuous family of optimizers. And in fact, there's lots of optimizers when you let the number of points go down even further. But there are two observations I want you to make from this example. First, you'll notice that, like, if you take some rando shift southward with this point, you're going to lose symmetry. You no longer have symmetry for this optimal packing, and that's by virtue of the fact that you can rattle the point south and exploit non-uniqueness in order to break symmetry. Another observation I want you to make is, okay, symmetry was broken, but what's preserved is partial symmetry. You remember partial symmetry arising in the context of the Erdős distinct distances problem. It's coming up here as well, where this guy, now that I think about it, he is invariant under reflection about the XZ plane. But let's focus on symmetric and orthogonal. So I can rotate to map this point to that point, that point to that point, and this point to left field. And that will be a partial symmetry. And in general, you shouldn't expect to get full symmetries from non-uniqueness. In general, this meta conjecture, I want you to put in your brain. So suppose you have a uniquely optimal code with low complexity. So I'm avoiding non-uniqueness, and I'm also avoiding complexity from the previous slide. Okay, I haven't rigorously defined low complexity just yet. That's why this is a meta theorem. Okay, so under this hypothesis, the code is necessarily symmetric. So he has a non-trivial symmetry. And furthermore, every optimal code of size 1 lower is going to be partially symmetric, which is to say he's going to have a non-trivial partial symmetry. Okay, so this is the meta conjecture. It's clear how to rigorize uniquely optimal and symmetric in these things, but how do you rigorize low complexity? So for this, we're going to lean on existing approaches in computational complexity. So a standard model in computational complexity is that an algorithm is computationally feasible when it can be computed in polynomial time. Okay, so one might be quick to argue that, hey, if the exponent in that polynomial is huge, like if your algorithm runs an n to the million, then maybe you shouldn't consider that to be computationally feasible. In practice, we frequently find that if there's a polynomial time algorithm for something, then there's a reasonable runtime version of that algorithm. So this is a thing that we're going to adopt. In order to adopt this, we need to not think about a single code as being low complexity. We actually need to think of a sequence of codes as having low complexity. So we want a polynomial time computable sequence of uniquely optimal codes. This is going to be the hypothesis of our conjecture. And we're going to call this a unicorn sequence, because whenever you discover one of these, it looks really special, like a unicorn, okay? So a unicorn space is going to be a metric space that admits a unicorn sequence. And then our conjecture, this is not a meta conjecture. This is where everything can be made extremely rigorous. For every unicorn space with a non-trivial isometry group, every unicorn sequence in that unicorn space, and every cone in the tail of your unicorn sequence, the following is going to happen. So your code is going to be invariant under some non-trivial isometry of the metric space. And furthermore, every code of one size lower is going to enjoy a partial symmetry. Okay, that's the conjecture. So once you pose a conjecture, one thing you might try to do is prove it. And in this case, you would have difficulty because there's lots of metric spaces, compact metric spaces. So the next best thing is to try to disprove your conjecture by looking at a bunch of examples. Is there a comment for me? Can someone, Emily?
Yes, Bill says polytime computable in what parameter size of the code, question mark.
Yeah, so right, the correct model here is annoying. So there are two considerations. One, you have to consider the precision. So these codes, or the metric spaces, you should think of as being continuous. So then you're going to have a representation of that metric space using binary strings and like decimal expansions, binary expansions of coordinates and what have you. So what you need is like a sequence of approximations to a code, okay, where you allow for the binary strings to get arbitrarily large. And what you want it to be polynomial time in is for a given code size with a given precision, you want the algorithm to be polynomial in the size of the output, right? In the size of the approximation to the code. So it would be like the number of points times the number of bits it takes to approximate the locations of those points. And that's the size of the output, and you want to be polynomial time in that. That's what we mean here.
Bill says thanks.
You got it. Cool. So once you have a conjecture, you might try to prove it. And when you can't do that, you try to disprove it. So we threw this at every example we could, we had the imagination for. And a subset is this table. There's some obvious examples like the interval or the circle. There's less obvious examples like the equiangular triangle, like the interior, like not the boundary, but the interior of the triangle. The hypercube, a bunch of other stuff. And we haven't been able to disprove anything. You'll see that it's actually non-trivial sometimes to tell whether something is even a unicorn space, let alone whether it satisfies part A and B of that conjecture in the previous slide. In general, it's easiest to prove that something's a unicorn space, and it's next easiest to prove part A, and it's hardest to prove part B. And the reason is that part B concerns all optimal codes of one size lower. And so you have to have a lot of control over, you have to have a lot of understanding of what these optimal codes even look like. I want to briefly discuss the question marks in here. So first I'll talk about the equilateral triangle. Then I'll open up these spaces, which are, you can think of them as tori, which is the plural of torus. Okay, toruses, receive the message. Okay, and then finally, I'll talk about unit distance metric trees. So let's start with the triangle. So this has been studied since like the 60s, like what's the optimal packing of points in a triangle? And if you have a triangular number of points, then there's an obvious packing that you should try. And it's known that this is actually the unique optimizer. You take the obvious intersection between your triangle and a dilation of the hexagonal lattice, and the surviving points form your optimal code. So you'll notice that this enjoys symmetries, like as a rotation, reflection symmetries, symmetries with the dihedral group of the triangle. So now you're wondering, what happens if I remove a point? It's conjectured that the optimizers for this are obtained by just removing any one point from the triangular number code. So that's a conjecture. It's unknown. I think it's known maybe for this one, but maybe the next one it's unknown, something like this. Like it's only known for finitely many codes of this size. So there's another conjectural unicorn sequence in this space. In particular, these folks conjecture that this construction is uniquely optimal. So what you have here are you have a triangle here, a triangle there, a triangle there, and then an upside down triangle in the middle. It's conjectured that the corresponding sequence of codes here are uniquely optimal for their size, but it's unknown if that's the case. If it were the case, then you'll notice that it enjoys all the symmetries, so it wouldn't disprove part A of our conjecture. We're not sure what happens when you remove a point from this. And no other unicorn sequences are currently conjectured to exist for this space. Okay. So that's the equilateral triangle. Let's talk about tori. So the big idea here is that if you have a lattice in Euclidean space that gives the optimal sphere packing, okay? So the hexagonal lattice gives you an optimal sphere packing in R2, for example. What that means is if you take an appropriate dilation of the lattice and then reduce modulo the lattice, you end up with an optimal code for the corresponding torus. So in this case, what this parallelogram represents is the fundamental domain of the hexagonal lattice. And then what these points are what you get when you divide the lattice by 1, 2, 3, 4, 5, 6, 7. Okay. So you end up with 49 points in the torus, and it turns out maybe it's believable by virtue of the lattice producing an optimal sphere packing. This ends up being an optimal code for this torus. Now there are other ways to shove a lattice into the corresponding torus. Sometimes it's possible not just to dilate by a factor, but also to simultaneously rotate in a way that maintains the periodicity, right? So here's another code of 49 points, and it's actually distinct from that code. Like there's no isometry of the torus that sends this to that. So these are fundamentally different codes for it. But there are some cases, in fact, infinitely many cases, where there is no such rotation to get you can prove uniqueness. So the theory here is that every code that arises from this process, we call that a lattice code. Every lattice code happens to be optimal. If a lattice code exists, every optimal code is a lattice code. And for the case of the triangular lattice, we can prove that there's a sequence of uniquely optimal lattice codes. So this is a unicorn sequence. It proves that the torus, the triangular torus, is a unicorn space. Okay. There are other types of codes in this world. Before you can understand it, I need to tell you what a deep hole is. This comes from lattice theory. So you're given a lattice in Euclidean space, find the point in Euclidean space that has maximum distance from the lattice. It's as far as possible from the lattice points. That's called a deep hole. And any point in Euclidean space of that distance from the lattice is another deep hole. So a holy code is going to be a code in the torus where any choice of representatives will have the difference set residing in the deep holes, union 0. Okay, that's what a holy code is. And holy codes are great. Whenever you have a holy code, it's necessarily optimal. If a holy code exists, every optimal code is necessarily a holy code. And we can prove that for the usual suspects of lattices. Holy codes exist for all sizes up to the smallest lattice code. So there's like a phase transition where you know the holy codes are optimal, and then you hit the first lattice code. So something interesting here is we actually don't know if D4 gives the optimal sphere packing in 4 dimensions, but we're able to prove theorems about codes in the corresponding torus. And this actually gives some evidence in favor of the packing being an optimal sphere packing. So from this, you can actually show that like an instance of part B of our correlate of our conjecture actually holds, that the smallest lattice code for these spaces is uniquely optimal, and every optimal code of one smaller happens to be, well, it's a subset of the lattice code up to isometry. And it's because of that, it has the partial symmetries that you would hope that it has. Notably absent here is the Leech lattice, because the Leech lattice was too big for our computers to do the computations we needed. Some open questions here that seem within reach is R8 mod E8 and R24 mod the Leech lattice. Are these unicorn spaces? That I'd be interested to think more about that. There's a general conjecture related to part B of our conjecture in the context of the triangular torus, which says that whenever you have a lattice code, what we call a lattice code, whenever a lattice code exists, all of the optimal codes of size 1 smaller are going to be obtained by just removing a point from the lattice code. And it seems like you should be able to prove that in the special case where the number of points is 8. But I have no idea how to prove it in general. Very quickly, I want to discuss this unit distance metric trees. So this is a very large family of metric spaces that are one-dimensional. So you should think one-dimensional means that coding theory is easy. So maybe you could like prove or disprove the conjecture in this space. Let me tell you what these spaces look like. So you're given a graph, so it's a tree with vertices and edges. Here's an example. And we're gonna glue together E copies of the unit interval like this to get a metric space. So you'll notice that this kind of looks like a straightened out version of this tree, and we have a distance along this metric space since it comes from the unit, like gluing a bunch of unit intervals together. So I have this metric space. You can think of what optimal codes look like in here. And there's an obvious one where you put a code point at each vertex of the original graph, and then you uniformly space more code points between those vertex points. You can prove that that's uniquely optimal. You can also prove that for these metric spaces, if you're uniquely optimal up to isometry, then you're actually uniquely optimal. Like forget about up to isometry, like you're the only one. So that's a useful feature. There's a linear programming story here. So you can actually find the all optimal codes of all sizes in unit distance metric trees by running a linear program. Actually, you're running a bunch of linear programs, but for a fixed metric graph, E is constant. So this is what you would call a polynomial time algorithm. So you partition your code into the size of your code into numbers that sum up to the size, and you're going to assign like TE members to each edge of the metric graph. Okay, so now I'm going to optimize the locations of these points subject to the constraint that I have exactly TE members of the code in each of these edges. And we can pose this as a linear program once I have enough code points. So we did a bunch of examples on metric trees on at most like 7 or 8 edges, something like this. And we were trying to disprove the conjecture. And for all optimal codes that we computed, they were actually uniquely optimal, except for these guys. So these guys, I'm drawing a red edge whenever the distance achieves the code distance, the minimum distance. So these 2 points here are you can actually wiggle them. There's some rattle here. But interestingly, despite the rattle, for each of these examples, there exists an isometry of the entire metric graph that preserves the entire thing. So it appears that not only is conjecture B true for unit distance metric trees, it appears as though a stronger thing is true, that you don't need to say partial symmetries. You just have honest symmetries, but we don't know if that holds in general. So I explained to you how symmetry implies optimality with some fine print. And then I showed you how optimality implies symmetry with some fine print. There's lots of open problems available here. And you can learn more about them in these papers. At this time, I'll entertain your